In this video, we're going to be looking at charge density for a sphere. And it's not just any sphere, it's a metal sphere, which means it's a perfect conductor and all the charge is going to go out on the outside. It being a solid metal sphere and a perfect conductor, charge density will be negative Q, because I decided it would be a negatively charged sphere, 4/3 pi, and then r cubed, where r is the radius of the sphere. Now here's something interesting. If I picked a smaller radius, like maybe halfway through the sphere, a, and I tried to calculate this, the amount of charge calculated at 4/3 pi a cubed, interestingly enough, this is 0, because I wouldn't have any charge enclosed in that region. Because remember, on a perfectly conducting sphere, all the charge lives out here on the edge, tries to get out as far away from each other as possible. Now, I can also, as we've seen in other videos, look at the surface charge density using the surface area equation for a sphere. So the surface area of a sphere is 4 pi r squared. I wouldn't do the surface area of anything inside the sphere because that wouldn't be the surface. That would just, it could represent a surface inside the sphere, but we're not going to do that. It'll give the same type of results as we saw up here, that inside this metal conductor that there would be no charge density. So I'm going to get rid of all this, and we're going to look at a perfect insulator, which I'm going to draw in white here in just a moment. So let's get rid of some things. Starting fresh, if I have a plus Q charged sphere that is a perfect insulator, that charge is just going to kind of be stuck and evenly distributed wherever it is it stays. So now, if I look at R and I compare that to maybe a shorter distance A, regardless of whether I am in this shorter distance A or R, because it's an insulator, I'll be able to calculate the charge density. Just like this. Not R, A cubed. So we'll have a smaller fraction of the total charge being contained here with this area. It's important to note that we're assuming a uniform charge density, so regardless of whether I take R or A, I'm going to be getting about the same amount of charge per unit volume. So it's not like there's going to be more charge lumped out here that I'm going to miss. It's a uniformly distributed charge density. So that's interesting enough, but now let's look at something a little bit different. I'm going to go ahead and clear the screen again. And in this one, we're not really going to calculate anything, not that we have been, but I want to look at what happens when you have a sphere of plus Q, and then you have a shell surrounding it, and that shell is maybe minus Q. And these are both going to be conducting surfaces. So it's actually going to be interesting what happens here, because all along this inner surface, they're not touching, those negative charges will be attracted to these positive charges that will attempt to get at one another through this region of empty space, but they're not going to be able to. And so what you have here on the outside then is a region that is effectively electrically neutral. So that if you circled the whole thing any readings of an electric field out here would be 0. This is the basic premise behind shielding, and you'll see that we do that with some of the wire examples, and it actually has applications in electronics where you put metal shields around circuitry to shield them from giving off their own electric fields that could interfere with other devices. So that's just some real-world applications there. But that's it for this video.